this thermocouple, and the thermocouple is basically soldered or welded here. And we have the fluid which is flowing at some temperature Tg, which we intend to measure. So basically, there are some heat transfer that is going to happen, which we're trying to analyze to predict what is going to be the error in the measurement. That means there is going to be a temperature difference between Tt and Tg, which we are going to find out from the thermal analysis. So we said that, first of all, there is a cylinder which is sticking into the flow, into the tube. And typically this kind of scenario, if you want to understand the heat transfer, you talk about the Nusselt number, which is a function of Reynolds number and Prandtl number. And the typical correlation is given as C, some constant, times Reynolds number to the power m and Prandtl number to the power n. And the value of C, m, and n would depend on Reynolds number and Prandtl number, as you can see in this table. Depending on the Reynolds number range, you can pick out the value of C and m. And the Prandtl number will decide what is going to be the value of n. So we are not neglecting the radiation heat exchange that takes place between the surface of the cavity and the surface of the tube. So this is the typical radiation heat transfer formula. This is the emissivity and Stephan-Boltzmann constant. And this is the temperature of the cavity at some x location, as we had seen here. In this some x, we are talking about what is the temperature. And then this is basically the tube temperature, the wall temperature, tube wall temperature. So we can linearize this using this approximation. We say that, okay, you take TW to the power 3 common and you get T minus TW. So this is called the radiation heat transfer coefficient, H subscript R. And then we can actually do a heat balance, taking a small control volume here. This is basically the control volume. So what are the exchanges that are happening? The conduction heat is coming from the bottom side. Conduction heat is leaving there over an element length of delta x. The convection heat is coming from the gas into this cavity wall, and the radiation heat is leaving from the cavity into the tube wall. Okay, so these are the different heat exchanges that are happening. So the convection here, heat transfer between the gas and the cavity wall is given by perimeter times delta x. So that is basically the area. Heat transfer coefficient, so H into A into delta T, Tg minus the temperature at any x on the cavity wall is T. Similarly, the radiation heat exchange is, again, the heat transfer coefficient is different. This is radiation heat transfer coefficient HR into area into temperature at any point in the cavity minus the temperature that on the wall. This basically. Then the conduction in is, this is from Fourier's law, Ka dt over dx at some x. And what is going out from this control volume is Ka into dt over dx, x minus delta x, right? So we need to basically, see what is coming in. The convection is coming in, heat conduction is coming in, and heat conduction is going out, and radiation is going out. So if you can write this energy balance, so conduction coming in, convection coming in is equal to the conduction going out plus the radiation going out. And all these expressions are here. So these expressions, if you just substitute here and you rearrange, you end up in this equation. Okay, so I'm not going to read out the terms. You can just see this is basically what we have written down here. So if you rearrange and you get basically this equation. It's a second order equation, d square t over dx square plus this term into T plus a constant time Tg plus a constant T wall is 0. Now, if you want to solve this equation, one way to do it is by non-dimensionalizing this equation. That is typically done in heat transfer when you are talking about, for example, extended surfaces like fin. You do a heat balance and then you non-dimensionalize the equation. So we are going to also non-dimensionalize. So here you define a reference temperature scale. And this reference temperature scale is defined by taking the gas temperature and the T wall temperature, and the heat transfer coefficient and the radiation convection heat transfer coefficient H and the radiation heat transfer coefficient HR. So this reference temperature is written as H into T gas plus HR into TW divided by H plus HR. So when you define this reference temperature, then you define a parameter theta, which is T minus the reference temperature. So when you do that, and you also define the effective fin parameter, which is H plus HR into P over KWA square root. So with these, when you substitute in this equation, you get a simpler equation. This is non-dimensional. So you say d square theta over dx square minus m effective square is 0. Okay. So this is the equation we need to basically solve. Okay. So you need a boundary condition. You say that when you go at x equal to L, that means at the tip here, you say that, okay, the temperature variations are not that much, it's negligible. So you say that dt over dx at x equal to L is 0. It's very close to the hot gas and the temperature variation will not be significant. So if you use this condition, then you can get a solution to this equation, which says that your theta T, which is basically temperature at the thermocouple tip minus the reference temperature, is going to be the wall temperature minus the reference temperature divided by cos hyperbolic effective fin parameter divided by the length of the cavity. And your thermometric error is always what you measure, that is TT, and what you intend to measure, that is TG, T gas. So the thermometric error is basically TT minus TG, which is basically your reference temperature will go to the right-hand side, and you subtract TG. Right-hand side, it will become positive. So Tref minus TG plus this term here, right? TW minus Tref divided by cos hyperbolic M effective L. And if you want to minimize the thermometric error, one way to do that is to use a design which gives you the M effective into L very high. So if M effective into L is, let's say, infinity, then cos hyperbolic infinity will give you infinity. And 1 over infinity will give you 0. That means this entire term will go. So only you have this term. TT minus TG is Tref minus TG. Now, you use a second condition. You also take measures such that your convection heat transfer coefficient is much greater than the radiation heat transfer coefficient. So in that case, so this is your definition of reference temperature. When H is greater than HR, you can actually neglect HR here. So when you neglect HR, you only left with HTG over H. That means HS gets cancelled. So Tref becomes simply TG. So this Tref becomes TG. So TG minus TG becomes 0. So that means your thermocouple temperature becomes equal to the gas temperature, right? So if you want to minimize the error, this is the condition that you have to use. Okay. Right. So we talked about basically we were discussing about thermocouple, and we talked about three different scenarios where we talked about how, depending on the temperature measurement field or the particular application, we may encounter error in temperature measurement when we do using thermocouple, and how we can minimize this temperature measurement error. Okay. In fact, you would encounter such errors not only just with thermocouple, but with many different kinds of temperature measurement sensors that we have talked about. But it just gives you an idea when you talk about, when you want to analyze, temperature measurement error, how you should really proceed. Okay. Now I shift gear and I talk about pyrometry. And pyrometry is basically the science of high temperature measurement. You are talking about measurement of temperature that are relatively high. Now, question is how high? So typically the temperatures above gold point temperature. Okay, the temperature at which gold melts is called gold point temperature. Gold melts at about 1064.43 degrees centigrade. Okay, so that is the melting point of gold. And any temperature above that comes under pyrometry. And the principle of pyrometry is basically based on the radiation, electromagnetic radiation emitted by a surface in the visible spectrum. Okay. So if a surface is at some temperature, it will radiate electromagnetic radiation. So out of that electromagnetic spectrum, how much radiation is coming in the visible spectrum, okay, in the visible wavelength, is what is important when we talk about pyrometry. So pyrometry is a non-contact method of temperature measurement because unlike thermocouple or thermistors and platinum PRT and so on, you do not physically put a probe there. Okay, so you use some kind of optical method to measure temperature, but without any physical contact. Now, the principle of pyrometry is based on black body radiation. So if you have studied radiation heat transfer in your undergraduate or master's and so on, or undergraduate, you basically would have studied about black body. So what is a black body? You would have encountered this kind of figure in your book. So a cavity of this kind, where the temperature, the internal surface temperature is constant throughout the internal surface, can be considered as a black body. Okay. So this black body, if you compare with a real body, if the real body and black body are at the same temperature, the black body will emit highest amount of radiation at a particular temperature. Okay. So as compared to real bodies, black bodies will emit the maximum amount of radiation energy at a particular temperature. Okay. So that is the definition of black body. So the black body radiation, how much electromagnetic energy comes out of the black body, is a function of two things. One is the wavelength. Okay. Different energy comes out at different wavelength, and the temperature of the surface. Now this is basically expressed by what is called the Planck's distribution function. Planck's distribution function is expressed as this: E B lambda at a particular temperature B stands for black body, lambda stands for at a particular wavelength, and T is temperature, is given as some constant C1, lambda to the power 5, 1 over e to the power C2 over lambda T minus 1. Okay. Now, your constant C1 and C2 are given as here. C1 has a value of 3.742 into 10⁸ watt micron to the power 4 divided by per meter square. C2 is basically 14390 micrometer into Kelvin. So C1, C2 have constant values, and depending on the wavelength and the temperature, you can actually find out what is EB lambda. Okay, and this is called the Planck distribution function. Now, this Planck distribution function, this function here, can be made simpler under certain conditions. Now, typically in pyrometry application, as I said, you are talking about visible wavelengths. So that means your lambda is about 0.4 to 0.7 micron or so. So say lambda is typically 0.66 micron. Okay, that is where you have the maximum visible wavelength intensity. And if the temperature doesn't exceed 5000 Kelvin, then the Planck distribution function that we saw here can reduce to what is called Wien's displacement function, Wien's distribution. So Wien's distribution is relatively simpler, okay? And EB lambda at temperature T is basically C1 lambda to the power 5 e to the power minus C2 over lambda T. So if you compare this with Planck's, basically you have neglected this. Okay, this term is so high because C2 is very high. Now, if and lambda is, we are saying, it is around 0.66 micron. And if temperature is not very high, this e to the power C2 over lambda T will be a very large quantity compared to 1. So that means you can neglect 1. So you basically get EB lambda T C1 over lambda to the power 5 e to the power minus C2 over lambda T. You can see this plot here. X-axis is the temperature going from 0 to 5000 Kelvin. Y-axis talks about the error. What is this error? Error is basically by going to Wien's distribution from the Planck's distribution, what is the difference between EB lambda T predicted by Planck's distribution and that predicted by the Wien's distribution? This difference is given here as percentage error. So you can see that even if you go to temperature is 5000 Kelvin, the difference between the two is only 1.2%. That means instead of using this relatively complicated formula, you can just use Wien's distribution with this simpler formula. Okay. The second thing that you need to understand is that the spectral blackbody emissive power, EB lambda, has strong temperature dependence. Okay. And this is the theory behind thermometry using the concept of blackbody. So if you plot EB lambda with lambda here, so this is your emissive power or EB lambda. Here it is lambda. Okay. And you can see that at about 300 Kelvin, which is about 27 degrees centigrade, or room temperature, around room temperature, the characteristic is shown somewhere here. Okay. And this is mostly around in the visible range. Visible range will be somewhere here. And if you go to a higher temperature, like 1500 Kelvin, this curve, EB lambda curve, is going to shift and look something like this. If you go even higher to 5800, the curve would shift like this. Now, if you look at for each temperature, there is a wavelength at which you get maximum power. So somewhere around here, you get maximum power at 300 Kelvin. Somewhere here, you get maximum power for 1500 Kelvin. Somewhere here, you get maximum power for 5800 Kelvin. Now, if you take the wavelength corresponding to the maximum emissive power, that is the lambda max, and multiply with that temperature for that curve, and you do that for multiple temperatures, multiple curves, it turns out that this lambda max into the temperature is a constant. And that constant has a fixed value, which is 2898 micron Kelvin. Okay. And this is known as Wien's displacement law. Okay. The lambda max T is 2898 micron into Kelvin. Okay. Now, so we talked about black body radiation, EB lambda, from Planck's distribution function. Then we talked about Wien's distribution. Then we talked about the Wien's displacement law, how spectral emissive power. Next, let us talk about the concept of brightness temperature. Okay. What is brightness temperature? The basic philosophy is that surfaces will appear brighter at a higher temperature. And this is the idea which is central to pyrometry that we are going to see. That means higher the temperature, brighter the surface. Mostly metals, in case of metals, this is the thing. And in pyrometry, mostly we measure temperature of metals. So one thing we learn is that higher the temperature, brighter the surface. The spectral emissivity epsilon lambda is defined as the ratio of emissive power of an actual surface to that from a black body surface at the same temperature and same wavelength, right? I said when I was defining what is the definition of black body, I said that black body is a body which emits maximum radiation power, radiation energy at a given temperature as compared to the real bodies. Now, when you compare the radiation of a real object with the radiation coming from a black body at the same temperature, of course, the radiation emitted by the real object is going to be lesser. Now, how much it is going to be lesser is going to be represented by the spectral emissivity, epsilon lambda. Okay. And how much it is going to be less compared to the black body is going to depend on the wavelength at which we are measuring the emissive power. Unless we are measuring the emissive power at all wavelengths, you can talk only about one wavelength or a range of wavelength, and the temperature. So your emissivity is defined as the emissive power of an actual surface or body at a given temperature for a given wavelength divided by the emissive power of the black body at the same temperature at the same wavelength. Okay. So this is known as spectral emissivity, which is at a particular lambda. Okay, so now let us come to brightness temperature. What is brightness temperature? Brightness temperature is the temperature at which the hypothetical black body spectral emissive power is same as the spectral emissive power of actual surface. Okay, let's say you have an aluminum plate and it is at some temperature, let's say 800 degrees centigrade. Now, what is the brightness temperature for this case? You have the aluminum surface and you can estimate what is the emissive power for a particular wavelength at that temperature of 800 degrees centigrade. Now, if you take a black body and there you say that if the black body is also giving away emissivity, the radiation energy, at what temperature the black body will give the same emissive power as the aluminum surface at 800 degrees centigrade, 800 degrees centigrade. So that temperature of that hypothetical black body is known as the brightness temperature. Okay, your object A is at some temperature T1. At what temperature a black body will give away the same power, emissive power, and that temperature of the black body is known as brightness temperature. So basically, emissive power of an actual surface at some lambda at some temperature should be equal to emissive power of a black body at that wavelength at some temperature, and that temperature is the brightness temperature. Now, already you know that emissive power of the actual surface at a temperature is epsilon lambda emissivity times EB lambda into T. And now from here, you say this is equal to EB lambda into TB. Okay. So you can very well see from here that since epsilon lambda emissivity has a value between 0 to 1, okay, because this emissive power of the actual surface will always be less than EB lambda. In the extreme case, when this actual surface happens to be a black surface, black body, it will become 1. And if this is very small, it will have a value close to 0. So this spectral emissivity has a value between 0 to 1. Since this has a value between 0 to 1, and emissive power is increases with temperature, that we have seen from this plot, right? As temperature increases, emissive power increases, right? So it's a direct correlation is there between temperature and emissive power. You can very well see from here that the brightness temperature will always be smaller than the actual temperature, right? Because you have epsilon lambda multiplied with emissive power at that temperature. So definitely TB will be less than T. So you can see this is verified here. Somebody has actually checked this. You talk about a surface whose brightness temperature is equal to gold point temperature. Okay, so there is a surface whose brightness temperature, and we defined what is brightness temperature. There is a surface whose brightness temperature is equal to the gold point temperature, which is nearly 1337.5 Kelvin. And the wavelength is at 0.66 micron. The actual temperature would be a function of the emissivity, spectral emissivity. When spectral emissivity is 1, the temperature is same as the black body temperature, the brightness temperature, right? 1337. As the spectral emissivity reduces, you can see that the actual temperature is higher, right? That means if you have some spectral emissivity and you want to know what is the actual temperature, if you know the brightness temperature, the actual temperature will always be higher than the brightness temperature, depending on the spectral emissivity. If the spectral emissivity is very small, the actual temperature will be very large compared to the brightness temperature. If the emissivity is relatively larger, then they will be comparable. Okay, so now we work with the Wien's approximation, which is this formula here. And we just express these things in terms of Wien's approximation. So when you do, the left-hand side is basically epsilon lambda into this one, which is C1 divided by lambda 5 e to the power minus C2 over lambda T, because this is at the actual temperature. The right-hand side is EB lambda TB. So that will be C1 over lambda to the 5 e to the power minus C2 over lambda TB. So this C1 by lambda to the power 5, C1 by lambda to the power will get cancelled, right? And if you take logarithmic on both sides, you can show that, so this is basically, first, if you take logarithmic, it will be log A into B. So you say log A plus log B. Then log of e to the power something will be just that exponent into log E, which is basically 1. So if you do that, you can show that 1 over T minus 1 over TB is basically lambda divided by C2 into ln of epsilon lambda, which is the spectral emissivity. This equation is known as ideal pyrometer equation. Okay. Ideal pyrometer equation, because you are going to measure the brightness temperature. If you know the wavelength at which you are doing the observation in the experiment, and you know the emissivity of the surface, you can actually predict the actual temperature. We will go through the experimental setup, but this is the theory. Okay. If you can measure the brightness temperature, how you can measure the actual temperature of a surface using this ideal pyrometer equation. Typically, there is a correction to this equation, because in the actual setup, I'm going to show you the setup. You'll see that the brightness temperature can be measured using an instrument called a vanishing filament pyrometer. And in the vanishing filament pyrometer, you would see that, as we discussed, the actual temperature will always be greater than the brightness temperature, or the brightness temperature is less than or equal to the actual temperature, because the spectral emissivity is less than or equal to 1. So in a pyrometer, the vanishing filament pyrometer, for example, there are going to be several layers of optics that we are going to use, several lenses that we are going to use. So that may introduce some attenuation of the energy that is coming from the target onto the observer. So you need to account for a transmission factor, tau lambda. So you can correct that in this equation. So when you correct the transmission factor, this will be multiplied on the left-hand side here. So eventually on the equation, it will be on the right-hand side. So you will have 1 over T minus 1 over TB will be lambda over C2 ln spectral emissivity into the transmission factor. Okay, there is going to be some loss that is going to happen, the radiation power loss at each of these lenses. So this is called as practical pyrometer equation. This is the ideal pyrometer equation. This is the practical pyrometer equation. Now this is the instrument. This is called vanishing filament pyrometer. So basically, 1 is the target whose temperature you want to measure. 2 is the fill lens. Okay. I will talk about the purpose of all this. 3 is the aperture and a gray filter. 4 is the red filter and the objective. 5 is the eyepiece and 6 is the observer. You are basically making observation here. 7 is a filament. We are talking about vanishing filament parameter. So this is the filament. 8 is the battery. 9 is a variable resistor. Basically, you control the current by varying the resistance. And A is the ammeter where you are measuring the current. In fact, this system will be calibrated such that this current would indicate eventually the temperature. Okay. But you are observing here for some reason that we will be talking. Okay. How you can do some adjustment by looking at this, and then whatever current you get, that basically is correlated against the temperature. So the field lens, the purpose of the field lens is to gather the radiation that is coming from this target. And we are trying to measure the temperature of the target. And this radiation then passes through an aperture here. And the purpose of the aperture is to reduce the stray radiation. So radiation from elsewhere should not also pass through this. Only that is coming through this field lens will be directed through the aperture. And you will also have a gray filter. The purpose of the gray filter is to sort of, depending on the range of temperature, it will only pass, the lambda, the incoming electromagnetic radiation within certain wavelengths. Okay. So this basically would adjust the range of temperature. Let's say you are measuring temperature of this, and there is another object here which is at a much higher temperature. The radiation from there should not influence the measurement. So you basically have that gray filter to sort of allow the wavelength of light relevant to the temperature. Then you have basically a filament here, as we discussed, and you use basically this aperture to focus this radiation that is coming onto this filament. Okay, and this filament is made out of tungsten, which is high temperature resistant, and the temperature of this tungsten filament is varied by varying the current that passes through this filament. Okay, and you have the radiation coming from both the target, that is 1, and the radiation coming from this heated filament, 7. Both actually pass through a red filter. A red filter, the purpose is that it would basically bring the radiation coming from this surface and this filament over the same wavelength range that is in the red region of the electromagnetic wavelength. So that you can really compare, this filament with the surface. And since you are observing the radiation that is coming from the surface, you are also observing the radiation coming from the filament. The radiation that is coming from the object forms the background. Okay, and the radiation coming from the filament forms the foreground. Okay, and you will adjust this current until the intensity of radiation coming from the filament and the background they match. And when they match, you would see that this filament will vanish from the field of view, from the background. And that is why the name is vanishing filament pyrometer. So you basically control this until the brightness temperature of this filament and the background are the same. So basically, this is what happens. If the filament temperature is higher than the background, the setting is set to be high. That means the filament will basically glow in the background. And if the filament temperature is lower, then the filament will look dark, and it is known as, the setting is called low. See here, setting is high, that means the filament temperature is higher than the background temperature. Setting is high, it is glowing. And if the filament temperature is lower than the background, it is dark. Okay, it is appearing dark. When the brightness temperature of the filament and the background are the same, you see that the filament will completely vanish in the background. Okay, and this is the correct setting. So this is the concept that people use for the camouflaging things, right? So if you match the brightness temperature of an object with the brightness temperature of the background, you can really camouflage structures. Okay, you will vanish structures just like that. So if the adjustment is such that the filament temperature target brightness temperature equal, the setting is to be correct and filament vanishes from the view. And typically you use a wavelength in the red region. So you have 0.66 micron using a red filter. And our eye has a typical response of between 0.6 to 0.77. So basically this is what you see. You have the red filter, which has a response that gives something like this. This is the transmittance coming from the red filter. This is the response of the eye. Okay, we observe maximum around this wavelength. So our interest is somewhere here around 0.66 micron is when the radiation is coming from the filament and as well as the background. Okay, and you try to adjust them and you vanish the filament from the background, and the corresponding current at which this happens, you basically record here, which is related to the temperature. Okay, so this is basically the principle of vanishing filament pyrometer. I will just take another couple of minutes to talk about IR thermometry. This is known as infrared thermometry. It is a non-contact type temperature measuring instrument. And as you know, the radiation that is in the visible, in your the radiation that the temperature that you measure using IR thermometry is not in the visible range. It is typically in the range of 0.7 to 20 micron. Okay, so typically if you have used an IR thermometer, it looks like this. Okay, and there is a light that is coming out, and this light, laser light, is not the IR that we are talking about. This is only for making sure that you are pointing at the right surface. This is just a guiding light. If you have so many structures in a complicated machine and you want to point out a particular surface, you use this laser pointer to point the surface. But what is coming from the surface into this instrument, that wavelength is in the range of 0.7 to 20 micron. That you do not see. This is not in the visible regime. Okay. So this thermometry, IR thermometry, is based on the Wind's displacement law that you see here. And here, as per this, we know that in the wavelength range 0.7 to 20 micron, So something like somewhere here to here, the peak will here typically, if you talk about higher temperature measurements, the typical temperature range that you deal with is a few hundred to 1000 Kelvin. That is where IR thermometry is used. So in that temperature range, typically the maximum intensity is observed somewhere in the wavelength range of something like this. So that is why you use IR thermometry, because in this hundreds of Kelvin to 1000 Kelvin, the maximum intensity is observed over the wavelength of, let's say, 1 to 10 micron or 0.7 to 20 micron. That is why you use IR thermometry. So the principle is this: every object will emit electromagnetic radiation. So you are pointing at this object whose temperature you want to measure. The electromagnetic radiation from this surface in the IR regime, the electromagnetic spectrum will have a large range. The radiation in the IR range basically is collected using this optics. This optics basically collects the wavelength coming from the target, and this may involve a wide range of lights, but you have an IR detector, and this detector is only sensitive to the infrared range. Okay, and then the signal is fed into an amplifier, because this IR detector basically converts the thermal energy into electrical energy. And this electrical signal may not be very large, so you use an amplifier and then a signal conditioner, right? And then an analog digital converter, and then finally you have a display. So this is typical of measurement systems, what we discussed in the beginning of the class. You have these elements, and then finally you have a display. So these are the structures that you would find inside an IR thermometer. Now, the principle is that, you have basically in this temperature range, you are operating at 1 to 20 micron. Now you are measuring the emissive power, okay? And you see that depending on the emissive power and the wavelength range, we say that the maximum power happens depending on the wavelength range at some temperature, right? So if you have found EB lambda, let's say you found an emitted energy, something like this. So then you have to construct, plot this equation that passes through this point, okay? Something like this. And the temperature corresponding to this curve would be the temperature of the surface. Okay, so that is how you use the Wien's displacement law, because you know the lambda. This is in the wavelength regime, and you know the value C1 and C2, and of course, you need to know the emissivity of the surface, because this is EB lambda. So you want to find EA lambda, because that is the actual surface. So your emissive power into this would give you the actual emissive power. So if you know epsilon lambda, you know lambda, you know C1, C2. So you can, if you measure EA lambda, then you can predict what is the temperature. Okay, so that is how IR thermometers work. So depending on the surface that you are pointing at, you must know the emissivity of that surface at that IR wavelength. Okay, so if you do not know that, then it becomes difficult and you may get erroneous result. Okay, so I will stop here. If you have any question, then we can discuss.
Recording stopped.